Back again. All right. Okay. Right, how's the heads doing? How's the brains? Have we gone to complete mush? Have we rejuvenated? Ready to go and remember what we've done before lunch? Any questions about the control systems on the fuel side? Because we're going to go through it anyway.
A lot of questions.
A lot of questions. That's good. Be a bit bored if there's no questions. Okay. No worries. We'll recap this quite a lot. We will recap. Not too worried at all. Okay. Before we move on to engine controls, so we'll recap pretty much what we've done for lunch. Then we'll see how time's doing, and we'll move on to the next part. So let's start one of the last parts, which was the amplifier. Okay. So what signals was this amplifier and spill valve getting? This part here. What type of signals?
Electric.
Yeah, getting a sensor from where? What's it looking for? If I hide this bit. So what's it looking for? It will only activate at a certain time. So what sort of sensors is it going to get an information from for a signal?
It's from LP speed.
Yeah. So we'll look at phonic wheels later on. A speed sensor will send a signal at an appropriate time. It could be maybe 105% or something, maybe too fast. And that will give a signal to the electrical solenoid, which is based on electromagnet. That will energize it, and that will open the spill valve. So the spill valve will increase more fuel into between the spill valve here to open it. That will open up and decrease the servo pressure. So if servo pressure decreases, what happens to pump output? What happens to pump output if servo pressure decreases? Does it increase or decrease?
Decrease.
Yeah, it has to decrease. Whatever happens to servo pressure, the pump does exactly the same thing. Yeah. So if servo pressure decreases, pump output also decreases. If servo pressure increases, pump output also increases. Oh, Prabin, I'm trying to get you in. For some reason, it's failing. And to there. No, that one. No. I'm trying to get Prabin to come in to the lobby, but it's not working for some reason. No, still not working. Strange. No, failed. If anyone else is able to access Prabin in, Prabin's come as a guest. It won't let me admit him to the session for some reason. No. It's still not working. Could anybody message Prabin to try and get him to log out and log back in again? It won't let me do anything with him, unfortunately. If anybody can maybe personal message him just to log out and log back in, that might work for him, possibly. Trying that. Okay, I'll keep trying. Anyway, yeah, so going back to the electronic amplifier, it is a signal. Amplifier will amplify the signal, energize a solenoid. Solenoid will open the spill valve. Okay, that will allow more fuel into the LP side, which will push against that spill valve, open the servo pressure, decrease servo pressure, decrease output. Okay, so an electronic version. Then the pressure drop control diaphragm, that senses the upstream pressure, okay, from on the HP pressure side itself. So if pressure increases here, okay, it's going to push down on the spring. So if the HP pressure increases because you've maybe closed the throttle, if you've closed the throttle, you're getting a back pressure going up the side here again. Okay, try again. And so that will push down, which means if we've got a back pressure, we don't need as much fuel. If we don't need as much fuel, then it's going to push this diaphragm down, open the spill valve, which will allow servo pressure to decrease. So again, if servo pressure decreases, then pump output also decreases. And likewise, if you open the throttle, well, then you're letting more pressure out initially to the burner, initial pressure drop. So the pressure drop will be sensed again on the top. The spring will overcome that pressure, push against the servo. Servo pressure will increase, and therefore servo pressure increases, pump output will also increase. In other words, provide more fuel to there. And again, the sense in the HP pressure will be pushing the throttle valve closer in line with the throttle control, allowing a bigger gap here, which allows more fuel out to the burners. Right, I don't know why it's not allowing. Okay. Yeah, I'm sorry, Prabin, but I can't get to admit for some reason. Okay. So somebody can tell me about the top capsule here, the evacuated capsule. What was another name for an evacuated capsule again? Anybody remember? Also known as something else. This one here.
Inlet pressure or?
Well, no. Before going to it, what was another name for an evacuated capsule? I gave it another name. It's also known as another name. Do you remember what it was?
P0?
Well, yeah, it's a P0 sensor, but what was another name for it? It was a vacuum capsule, or also called a something else, or also known as. Anybody? No, also known as an aneroid capsule. Remember that? Aneroid. So evacuated capsule or an aneroid, in other words, it's sealed with sea level pressure, okay, as we're sitting on the ground. So it's a completely sealed unit, which will obviously expand or contract with pressure or indeed temperature. Higher the temperature, it's going to heat up the gas inside, expand it, and likewise colder temperature, it will contract it. Higher altitude means decrease in pressure, so the capsule will expand, and as we come back down to sea level, obviously the pressure is going to increase the closer we get to sea level, so we'll contract the capsule. So if we're coming down from altitude, we're getting to thicker air, so heavier, denser air. Well, that's going to contract the capsule, so more air means we need more fuel. So as it contracts, it will bring the lever up, which will close off the servo pressure, which will increase servo pressure, therefore increase pump output, providing more fuel because we've got more air. So that was P0. P1, well, P1 capsule, it is open to intake pressure. So the only thing that's going to affect that, really, well, you could argue a bit of temperature of the day could expand it as well. Warmer air getting pushed into air, but the main one was the forward speed of the aircraft. Yeah, so like a balloon, the more air you put in the balloon, the more it expands. So with an aircraft, the faster the aircraft's moving through the air, the more air is getting rammed into the intake. So therefore, P1 will increase. Well, if P1's increasing, well then the capsule will also increase or expand. Well, if we've got more air going in, that means we need more fuel. So with expanding capsule, the capsule pushes the spill valve up, closes off the spill valve, so there's no more bleed of servo pressure. That means that the servo pressure fuel will build up. And if servo pressure builds up, then it's going to push the piston down to increase pump output and increase more fuel to the burner. Because we've got more air means more fuel. Okay. Then we move back on to the actual pump itself. The actual piston pump, variable displacement, so it compensates for all this that's going on here: altitude, temperature, pressure, and demand of the pilot on the actual throttle. Okay, and remember what controls the pressure within the pump. What was the controlling component that controls the pressure within the pump? Anybody?
No.
What controls the pressure within the actual fuel pump?
Governor.
The governor. Yeah, the governor's in charge. There's always a governor in charge of anything, isn't it? So the old mechanical governor, calibrated spring. Okay, there will be a diaphragm across there, just like a membrane. Okay, so you've got LP pressure in yellow and the pressure within the pump itself. If that pressure exceeds too much, in this case, the way the diagram's at the moment, will push down on this valve. That will push down on the pivot point, which will open the servo valve. So if that opens the servo valve, then it's going to spill out servo pressure. Well, there we go. If servo pressure decreases, then pump output also decreases, and therefore the pressure within the pump will also decrease and go back to where it should be. Problem that could occur is we could have damage to the diaphragm. Maybe some bit of debris got in there, maybe damage the diaphragm, so it won't work properly. So what could happen then? How do we stop the pump from blowing up? Because if that's got a hole in it, it can't push down on the spill valve, which means it can't open the spill valve. So what helps open the spill valve if the governor fails? Anybody remember? No. Okay, we had the centrifugal drillings. So as the LP pressure, we have governor pressure mixing in with the LP pressure. Well, remember the spill valve, there's always a little gap between the spill valve and the servo line. It's never fully closed. So what will happen is the LP pressure will start to build up, which will squeeze in between the servo spill valve and the servo line. That will open the spill valve, and therefore that will decrease the servo pressure, which will decrease output. Okay. Eventually, though, what will happen, the spring here will try and push the servo valve back down, so you get what's called a hunting effect, where the engine's going up and down, revving up and down. And then so it's up to the pilot to recover that, reduce the throttle or such like. Okay. So again, main thing to remember, if servo pressure increases, pump delivery also increases. If servo pressure decreases, pump output also decreases. Whether it's the spill valve within the pump, or it's a spill valve in the control for pressure and that sort of thing, or it's because of the pressure drop control diaphragm, because of the movement of the throttle, or it's to do with speed of the actual engine and the heat at the EGT at the back of the jet pipe, all working together to control the right amount of fuel flow under the right pressure at the right time on selection of the throttle. Okay. So going back to a standard throttle, it's just a flow control valve in effect. But with a dashpot throttle, we have this control valve, which is attached to the main throttle lever, inside another throttle valve. So a valve within a valve. So remember, the control valve will move first, and then depending on the pressure in here and depending on the pressure in here will determine how fast the control valve moves with the main throttle valve, which again will determine how much the gap opens to allow your high pressure fuel to go to your burners. I'm trying Prabin, it just won't seem to admit you for some reason. Trying again. Okay, right. Any more questions on that? That's just a quick run through of what we've done already. Again, we'll go through as many times as you can. Any questions from everybody at the moment? Do you want to go through before we move on to the next part? Because we'll take our time. This one's a lot to understand, and I appreciate that. So I can go back to separate diagrams as well. Make sure you're happy with that one. Started. A standard pump would be a spur gear pump. So there's no variable displacement. It just goes as fast as the gearbox is spinning. So it provides a flow perspective of speed of the RPM pump, the gearbox. The variable displacement one, as we said before, the governor's in charge of the pressure. We do have the centrifugal drillings, which will work against with the governor. The movable cam plate, which moves backwards and forwards, which will, as it moves further deflection towards outside, that will draw more fuel in. So when it spins round, it will then push more fuel out. Okay. Once it's stabilised, it will go in the neutral position. Okay, null position where there's no, it's just quite steady. And then if it wants less fuel, it will push forward in that direction. Okay, because of reduced servo pressure. Servo pressure was just a tapping from your high pressure stream. And with the restrictor there, you'll have a higher pressure here or low pressure depending what's happening with the spill valve. Okay, when it's in balance, that colour and that colour are pretty much the same. Okay, but we've just highlighted it in blue to show you the difference in lines. Servo piston also has a spring trying to push that piston across. So when the engine shuts down, there's no fuel pressure, so that spring will push the piston across. So when the engine starts to spin slowly, it will provide fuel at the right time. And then once the high pressure system builds up pressure, that will push against the servo piston to a nice sustainable spot, waiting for the input from the throttle. So again, if the throttle's open, we get a decrease in the upstream pressure. So we get a decrease in upstream pressure, then this is going to decrease eventually through the differential control. It will push the piston across to increase fuel demand to deliver more. In other words, it will drop servo pressure to increase pump delivery. And I said there before, the governor always controls the pressure within the pump. Okay, so if it exceeds too much, it will push on the diaphragm, push down on the spill valve, which will rock open. That will spill off servo pressure. So if servo pressure decreases, pump output also decreases until we establish where it should be. Okay. And I'll just put the animation up again, just to see it working again. Although this is a hydraulic pump, it was one of the closest animation I could find, but it works in the same principle. The hydraulic pump wants back to front. But just like see animation again. Forward a little bit. Okay, so there's your cam plate, swash plate, which moves backwards and forwards, depending on the position of the piston, the servo piston. Drive shaft, obviously, to spin the swash plate. There's a servo spring, which in this case, the piston's actually at the top and the spring returns the bottom. But in our case, we've got a combined piston and spring together. And that's the mechanism that actually moves the cam plate into position. And there's the drum with the outputs and inputs of the fuel, in this case the hydraulic oil. But it's the same principle. Yeah, put it all back together and we'll see it spinning round again. And so you've got flexible ends on those little cylinders that will move depending on the angle of the cam plate, which will then have an input side and an output side. So some of the pistons will be drawing the fuel in, and as it goes round, it'll be pushing it back out, depending on the angle. So in this case, they've got the fluid coming in from this side. As it gets drawn in, and it gets pushed out because there's less gap at the top there. See the angle of the cam plate there? So more of an angle here. As it comes out the top, it pushes it further out. That increased distance gives the high pressure. So there's the kidney sort of shape I was on about when I was trying to draw the diagram. Okay, inside is LP and outside is HP. So drawing the fluid in and pushing it out. So that's maximum deflection at the moment. And then when it stabilizes, it will be positioned into a more neutral position. If you remember right, it does now. So there it comes to the more neutral position, so almost even sort of flow. So the spring's reacting against the servo piston. So it's pretty much there by now, totally even, so it's waiting for an input. So we can, in our case, we pretend the throttle is getting opened. So the throttle is getting opened. We've got a decrease in upstream pressure. We've got an increase in servo pressure. So more fuel, and then more fuel going back out. Okay. It's just this diagram shows you springs separate from the actual piston, where ours has got it on the same one. Okay. So a little bit of animation there. We mentioned the governor. Remember the centrifugal drillings, which are calibrated. So if the governor fails because of a rupture or a hole in the diaphragm, the excess pressure will build up on the LP side, push underneath the ball valve, and then open the ball valve to release servo pressure, which again will release delivery pressure. Two types of spill valves. We've got the half ball valve. Okay, now there's a little gap, always a little gap there on a pivot point, just like a seesaw. Okay, so down here, the governor would be pushing up or down against it. And likewise, the atmospheric control one, or your P0 or your P1, will be the pushing down on the valve or pushing up on the valve. Yeah. And then servo pressure, again, just a tapping from your HP side. Other type of valve we looked at was kinetic knife valve, like a knife going into the stream. So when the knife is in, it's cutting the stream, so it's bleeding. If it's bleeding, that means it's reducing servo pressure, which therefore it must be reducing pump output. And that's shown here by the servo piston moving to the right. In other words, the spill valve is open. Spill valve closed, well, that means servo pressure is now increasing, okay, which is now we've got a decrease in upstream pressure. Servo pressure is increased, pushes the piston across to push the cam plate to draw more fuel in, to put more fuel back out. Then intermediate place with the kinetic knife, it's halfway in, halfway out, so it's balanced. The cam plate will now be in a neutral position, waiting for an input from the pilot. Okay, so that's your kinetic knife valve. So half ball valve and kinetic knife valve are all types of spill valves. As we saw there, rubber capsules, P0, P1 for altitude, pressures, and also indeed temperatures. And then intake 1 was your P1, so for ram effect. The greater the air, more air means more fuel. So if we need more fuel, we shut the valve off, the spill valve, we stop spilling fuel out, we need to increase servo pressure, we increase servo pressure, we increase delivery pump output. Pilot's input, again simply the HP cock and LP cock, which is normally open. You can see the three positions there. So HP cock open, that will allow fuel into position, start or wherever, depending if it's a combined throttle lever, and off to the main burners as well, as appropriate. I can see there's actually a little pressure distributor weight, okay, which will only open once there's enough speed or enough flow from the fuel. So when you shut off that spring will actually push back and cut the fuel off to the burners once there's not enough pressure in the system, obviously when the engine shuts down. Back to throttles, simple throttle, just forward and backward, increasing the size of the hole for the fuel to come into or decreasing it. So not really a smooth operation. It will work, but again, if you move it too fast to open or again too quick to close it, that can cause potential too much back pressure or not enough fuel in the first place. So by using the dashpot throttle, we had the normal control valve, as we saw before, with the extra throttle valve surrounding it, controlled by a spring, throttle servo pressure, again, pushing against the actual throttle control pressure. Depending on the pressure in each one will depend how quick that catches up with the control valve. So it's just a dampener, a far smoother reaction. So it doesn't matter what the pilot does, because the mechanical system will kick in and either bleed off fuel, increase fuel, proportional to the pressure in the system. So it helps prevent overfueling and indeed underfueling. Just increasing the initial acceleration and then fully open. So now you can see the gap where it goes to the burners is now fully opened. Okay. And then once the pressures settle, these will stay in certain position. And your pressure drop was mentioned already. We'll go through it once again though. Is anybody not sure about the pressure drop control? This part here. Is anybody not too sure about that one? Anybody not too sure about the capsules here? Again, we'll cover it again later on. I'm just trying to go through it again twice at the moment. Make sure you're happy. End of the day, they're all fighting against each other to either open or close the spill valve. And if any spill valve opens, all it's going to do is decrease servo pressure. So if you decrease servo pressure, you decrease pump output delivery. Okay. This one here was only sensing the upstream pressure. So when you open the throttle, you're going to decrease pressure initially, okay, which will allow the spring to push the diaphragm up, close off the spill valve to increase, because you've opened the throttle. In other words, you want more fuel. That will, to get more fuel, we need to increase servo pressure. So we close the spill valve because the spring on this diaphragm is pushed up, close the spill valve, and then increase servo pressure. Increase servo pressure, increase pump delivery. And likewise, when we close the throttle from high RPM, you'll sense a higher pressure here, which will push down against the spring pressure, which will open the spill valve, which will decrease servo pressure, which will decrease output. Okay, that's all that's going on there. Right, and as mentioned already, electronic control as an optional extra. LP speed, so the speed of LP, if it's getting too fast. The only reason the LP spool will be going too fast normally is because your HP spool is going too fast. Because remember, the LP spool is getting the gas from the HP. Well, if the HP is going too fast, then the gas flow is hitting the LP next, which is making that spin fast, which in turn is drawing more air in. Drawing more air in means more fuel. So we're going too fast somewhere for whatever reason. It could be the governor has failed, okay, initially, quite catastrophically. So if it senses that at a predetermined level, a signal will be sent to it via an amplifier. Amplifier will energize that, open the bleed valve, decrease servo pressure, decrease pump delivery. Okay. Whether it's EGT sensor for exhaust gas temperature or the speed of the spool. You probably imagine that if the spool is going quite fast, then you probably find your temperature is getting there quick as well. Okay, so whichever one gets there first will signal that amplifier to open the spill valve. And then to finish off the whole basic system, we join it all together, and that's what we end up with. Okay. Okay, right, you guys, any questions from you guys again? Let's check if there's any part you want to go through again before we move on to the next part.
If the spill valve is closed,
yeah,
the pump servo pressure will increase.
Yeah.
Okay, so in upstream of throttle, pump servo pressure will increase.
Yeah, it would depend what section on. Yeah, if you're on about the spill valve here.
Mm-hmm. Yeah, I'm talking over right there. Yeah.
Yeah, good. Okay, if the spill valve is closed here and it's to do with the throttle pressure, we'll forget about ambient pressure, temperature, and ram speed. If you're looking at upstream pressure, which will be up here, obviously, well, if the throttle's closed, that means that we're wanting more fuel, because if the throttle's closed, we're going to get a backstream. Sorry, if the throttle's closed, if you come from high speed, then you get a back pressure, so the spill valve will open. But if you're saying the spill valve's closed, what's happened is we've had a drop in pressure upstream, which means now the spring pressure can push up the spill valve to close the spill valve. Okay.
All
So
right.
imagine you've opened the throttle, so you basically open the hole. Okay, so it will open initially. That will drop a little bit of pressure upstream because this is downstream. Okay, so the pressure in this line will drop a little bit, which will allow the spring to push up that valve and close the spill valve. And then, as I said, as we close the spill valve, servo pressure will increase, which pump output will increase. And then it will establish to whichever point that throttle was put. So that's just sensing the pressure drop between upstream and downstream. This would be a downstream, this sort of colour here, and the red is your HP is upstream. Yeah, upstream closer to where the pump is. Okay, downstream is effectively after your throttle control. Upstream is before your throttle control. Does that make sense there?
Yes, sir. Thank you.
Good. Anybody else? Don't be afraid to ask a question. It's your time. Make sure everybody's happy because it is quite a lot to take in. It takes a little bit of time just to join everything together to understand what's happening. Okay. This is just a basic system. This is one that, to be honest, these sort of diagrams and systems is pretty much the same sort of system I got taught back in, oh my goodness, you look in the early 90s, 1995, 96, so it shows how long ago I got the same sort of diagrams you're getting now, because it's still pretty much the same. Okay. So any other questions, guys, before we move on? Or are we all good?
LP fuel is from fuel tank.
Yeah, LP fuel, yeah, it's a low pressure system. So you're looking at your fuel tanks, your fuselage tanks, maybe underwing tanks if it's a sort of military aircraft, or even the fin. Something's with fuel in the fin. Now, the only thing that allows the fuel to go to the engine is the LP cock, the LP shutoff valve, which is your half ball valve. It rotates 90 degrees. Okay, and that's behind the firewall or the main wall before the engine. So we can use that for two occasions only: emergency and maintenance. And for maintenance, it allows us to disconnect the engine and remove it without draining all the fuel. Because imagine a big 747, we don't want to drain all the fuel. We'll be there for ages just to take an engine out. Okay, so we can isolate the fuel from the engine by using the LP cock, which is normally open, but in case of emergency or for maintenance only, you can switch it off. Okay. And that's represented by your yellow sort of colour there. Okay. Anything else? I guarantee somebody's going to ask a question, but the other person wants to ask it as well. So don't be shy. Ask away. Make sure you're happy, because it does, as I said, this takes a bit of time to go through it. But we'll go recap each day. We'll recap as we did with book one as well. I'll be asking plenty of questions. Happy to move on to the next part, or any other questions before we move on?
Move on.
All good?
I think we can move on, yeah.
Yeah, okay, good stuff. Again, we'll do lots of recap, so don't worry initially for today. It's a lot to take in. Right, we're going to move on to engine controls. Okay, and we're going to look at things, obviously controls depend on the aircraft. We have one engine, two engines, four engines, whatever the type of aircraft it is, all from the control quadrant. We call the middle part the quadrant, where all the parts move, flaps and etc. HP cocks. LP cocks tend to be in the roof or the side, it depends on the aircraft type. However, you can imagine things like a big aircraft, a lot of vibration, especially in turboprops, big propeller aircraft, they've got a lot of vibration. Now, if you're an engineer doing a ground run to check performance of the engine, you're busy looking at all the gauges, taking notes. The last thing you want is these controls starting to vibrate and shaking down the way, which can alter the numbers. So we can add friction dampers, which sort of lock the levers in position. And this is to help prevent what's called control creep. We saw creep before, the stretching of the blades. Well, this time, for the sake of engine controls, we call the creep of the controls starting to shake back towards maybe idle. In other words, moving when we don't want them to move. So by adding these little friction controls just help lock in the position. Obviously, don't use them when you're flying, but can help reduce them from vibrating on the ground. Okay, so that's control creep. Just stops the controls moving when you're doing functional checks. Another control we've got is the auto throttle. And auto throttle, that maintains constant speed during localizer and glide approach phases of auto landing. Nowadays, everything's pretty automatic. We hardly ever need a pilot. It's so automatic. The pilot's there to start the thing up and eventually land. Everything's pretty much automatic. So the pilots have got the easy job, really, haven't they? There's a lot more to it than that, obviously. But yeah, auto throttle, constant speed during localizer and glide approach. It also closes both throttles at a constant rate during a flare. Now, a flare is obviously when you're landing, you've got the aircraft flaring down the runway. Okay, so we don't want two engines doing two different things. We want them working together. So sometimes you might have seen on certain programs, you'll see the throttles moving themselves. Okay, but it's automatic pilot or auto throttle for landing and takeoff. Okay, it just takes the extra load off the pilot. Now, the pilot might have his hand there ready to take over just in case something electronic goes wrong, obviously, just in case they have to be there. But again, that is auto throttle. Okay. Right, control rigging. Now, rigging is when we have a control lever. We might be using Bowden cables, teleflex cables, rods, whatever sort of mechanism to actually physically move a control in the actual engine. Now, in a small aircraft, it's quite a short distance, but in a big aircraft, you remember the old days, that's a lot of cables, that's a lot of rods, and there's a potential for a lot of play. So rigging needs to be 110%. And remember as well, if you ever disconnect any controls for flying or engine or any sort of control, you must have what's called a duplicate check. It's a check upon your check to make sure that it's 100%. With rigging, what we're also ensuring is when we move a lever, it moves in the correct way and the correct amount. Now, with reference to engines, when you set up a rigging for a throttle lever, you always set up the maximum stop on the engine. In this case, the fuel control unit, the controller on. We always set the engine up first, and then we set the throttle lever next. Because if you set the throttle lever from idle to max and adjust it there, you're not guaranteed you will get maximum throttle on the engine stop. Okay, so we always make sure the engine will move fully to maximum first, and then we match the throttle lever to match that condition. And we get what's called a throttle bounce, where at the end of maximum travel, you do get a little bit of bounce, yeah, just a little bit of pressure. Obviously, it's a bit strange nowadays because everything is fly-by-wire, but we still allocate a little bit of mechanical throttle bounce. That gives the pilot confidence that, yes, we are within the correct requirements, the correct tolerances, and I can guarantee when I put my throttle forward, I am hitting the maximum stop on the control on the actual engine side. So, typical control rigging, bits of cables, 5-wire, whatever it is. With the control disconnected at the engine, you'll set all the adjusters halfway, just as a datum point, just somewhere to start from. At the cockpit end, you place the lever at the forward position, and then back it back about 1/8 of an inch to have a little bit of a gap. Okay, so we'll set it, that's just to give us a datum to work with. You'll put what's called a rigging pin. Now, a rigging pin is just a calibrated bit of rod that goes in a certain hole when the throttles are in a certain position. Okay, in this case, the lever in the quadrant. Then you adjust your control cables or rods as necessary to enable the fitting. So by using turnbuckles, we'll move the cables back and forward, okay, until all the rigging pins are in position on each control run, as indicated by the manual. So the rod's just coming in. And ensure that all adjustments remain in safety. And what I mean by safety is, when we look at turnbuckles, you've got 2 threads on one side, and you've got an adjuster in the middle. Now, you should be able to see the threads within the inspection holes. If you can't see the threads, that means that adjustment mechanism is not in safety. It could mean there's only half a thread holding that together. Okay, that's using like a turnbuckle. Then you set the engine control against the maximum stop, and then connect the last airframe link. So you've sort of preset the throttles in the cockpit, but you've not connected the rod to the engine yet. You then set the engine to maximum stop, and then now we connect the control cables or rods, whatever it is, to the actual throttle movement. If the last airframe link is not aligned, you adjust the length of the last airframe link, not the throttle end of the engine. It's the airframe side, or adjust the lever on the engine, depending which one it has to be first. Then you check all your control connections from the engine to the cockpit control lever for safety, correct assembly, locking. Make sure nothing's touching where it shouldn't be touching. And then once you're happy, again, that would be a duplicate check. You remove the rigging pins. And then you do a full functional, but even before you start the engine up, you do a full free range movement. In other words, does it go from idle to maximum, nice and smooth, and does it hit the stop where it should do? And you'll repeat that a few turns. And does it feel correct as well? Has it got the right sense? Is it too hard? Is it too light? Is it gritty? Is it not moving at all? Is something completely wrong? And then should an engine run be required? You do it now. Any adjustments required should be carried out at the engine end. Okay, so you might have to tweak the engine at the end. Even though the rigging's correct, you might have to tweak the actual fuel pump, the fuel control, the governor, etc. But as long as you can guarantee that the levers that move the throttle are 100% right position within safety, then yes, you can tweak the engine afterwards. But as long as you ensure that you're hitting the maximum stop on the engine first. As I said already, when all the work has been completed, the work should be certified and submitted for duplicate inspection. So you'll carry out all the work, you're happy everything's working right, then somebody will carry out a duplicate inspection. A duplicate inspection is somebody who's not been involved with the task at all. It could be a supervisor, it could be another authorised engineer, will come and check the work you've done. It's not checking you're a bad engineer, it's just a 200% check, because obviously it's very crucial that it is correct. Now, to move control rigging, we've got length and radius. Now, on your controls there, if we change the turnbuckle and extend the length of that turnbuckle, we change the length. Now, changing the length changes where the throttle stops and starts. Okay. The radius is how much that moves, okay, the range. So what we're looking at there is changing the radius changes the range. Let's say this point here to that point there was, let's call it 100 millimeters, okay? If I change the radius, this part here along the slide bit, I can maybe make it 80 millimeters or 120 millimeters, whatever, okay? Once I've set that, so there's my arc, there's the arc I've given it. If I now change the length, I can change that whole part when it stops and starts. So changing the length changes where the range is on the throttle lever. And we use that change in length to make sure that all the throttle levers are in correct alignment in accordance with the manual. Okay. So looking at this one, we've got 4 engines. So number 1, number 2, number 3, and number 4. Okay, now you can see here that, yeah, they've been properly put out of alignment. This is a stagger check. Ideally, you want all the throttles in line. So if you find that, like for example here, number 3 is way out, you would change the length, and that would bring that one down in line with these ones. And likewise, you would do the same with the rest of the throttles. The radius changes the range, how far that travel is, but changing length just aligns them up. Okay, you don't want throttles all over the place. Once you're happy that all the control rigging is done, and you are happy that the movement, the range of movement, the radius is all fine as well, the length is all good, then you need to check how much effort is required to actually move those throttles. And we call that the breakout or pull-off checks. And you'll use this sort of equipment on wipers on windscreens as well. Basically, like if you go fishing, you might wear fishing this. Use the same sort of equipment called a spring balance. You'll put it onto the throttle and you'll gently pull it. And once the throttle lever starts to move, you will read off the scale. Okay? And that will tell you how much effort is required to move it. Now, normally, effort needed is usually between 1.5 and 4.5 pounds-feet. Depends on type of installation. Okay. Could anybody convert that into PSI, what would 1.5 pounds-feet be in PSI? I mention it now because when you're doing torque setting, you need to be able to convert between pounds-feet and pounds-inches and pounds-inches into pounds-feet, because sometimes you get a torque wrench that might be carbon in pounds-feet, where the setting in your book is in pounds-inches. If you get numbers mixed up wrong, that can cause a lot of problems. So just a bit of fun. Who can convert 1.5 pounds-feet into pounds-inches? Who's the mathematicians here? Just for a bit of fun.
18 and 42.
18 point
18 and 56. 54.
Pick a number.
18.
Yeah, first one is 18. That's correct.
Yes.
18 PSI, and the next one would be
54.
54. Yeah, because there's 12 inches in a foot, so pounds-feet is simply multiplied by 12. Yeah. If it's pounds-inches, you just divide by 12. Not so bad here. Usually these will be calibrated in whichever, probably both. And as long as you're happy with conversion, it's not a lot. I mean, 18 pounds-inches, that's not a lot of pressure, is it? Again, the bigger the lever, you don't want the lever being so tight. You've got two hands in there trying to push it back. It should be a nice positive feel forward and backward. Likewise, you don't want it too slack here, but it can just flop about. Okay, because that can obviously be quite dangerous when you're flying. Okay, so normal effort, roughly about 1.5 to 4.5 pounds-feet, using a good old fish balance, spring balance. Okay, and you can use this equipment, as I say, on window wipers. Some aircraft have the window wipers. You can put that on the window wiper arm at a certain point, and then pull the window wiper arm, and that can also give you how much effort is required to pull that away. In other words, is it touching the windscreen? So you can use it for multiple things, as well as for weighing fish if you go fishing. So along with brake off or pull out checks, you've also got the throttle lever bearing checks. Now with this one, throttles are normally fully manual and must be checked as follows. So what you would do here is we're checking in the quadrant. Obviously these throttles move on a lever. That lever has a bearing at the bottom, so all throttle levers will have a bearing beside them. Now they're all very close to each other. So what we do to check it is make sure they're not rubbing against each other throttle, because that could cause problems in flight as well. So what we do is we place both or all throttle levers into the mid travel position. So that's 2 engines or 4 engines, we put them in the mid position. So we can go forward and backwards. Then we'll push one lever fully forward. We'll probably start on the left-hand side, number one lever, it makes sense. We'll push that nice fully forward, just take your time. And then with very light finger pressure towards the other lever. So now we're going to push it, not going to push it back and forward, we're actually going to push it to the side a little bit, just a little bit of pressure, not too much. And then we'll bring the throttle back. So we're pushing to the side and bringing back at the same time. And all that's doing is checking that the bearing isn't touching the bearing on the other throttle. Okay, if it touches the other lever and passing the bearing, it's defective and needs to place, because if it's worn, by pushing on the lever, it shouldn't touch my hand. Say I've got 2 engines here, my hands are the levers. If I push one over, it goes back and forth, it's great. But if I push it over and it touches that one, it's going to move that one as well, which we don't want that to happen. Because when you put your hands on throttle, there will be a little bit of play left and right on those throttles. Not a lot, should be pretty much nothing, to be honest. But they will wear out eventually, and they can catch the other throttle. So again, that could cause problems in flight. And if you find again, if that happens, you have to replace it. Now you do the same check for each throttle. So you do number 1 throttle, side, back. Does it move number 2? No, good. Put number 1 back again, put number 2 up, same again to check number 3. 3 up, check again, and so on and so on. As it says there, repeat with the other levers as required. And I mentioned duplicate inspection, just to finish off that part. So an inspection first made by one qualified person and subsequently made and certified by a second qualified person. Now that could be a fellow engineer, as long as they've not been involved with the task in hand. It's usually the supervisor will come out, but again, depending on how many people on aircraft, like myself, we used to call them independent checks. For you guys, we call them duplicate checks, the same thing. I would send my guys out to do a job, and if it involved control rigging, they do the job, they give me a shout, okay, we've finished the task, we're happy with it, I go and check it, and because I've not been involved in the task, I'm just doing the paperwork, I'm just going to the final part to go and make sure that it's okay. If it's not okay, we redo the paperwork to say to be adjusted again, and then carry out another duplicate check. We don't sign the duplicate check off until we are 100% it is okay. And this sort of typical example. So a couple of engineers going, working away, maybe working on controls, and he's come down to check the control rigging. Okay. Duplicate inspection. All right, that's the end of that section. Any questions so far on controls?
Not yet.
Not yet. That's slightly easier than the field control side at the moment, isn't it? Okay, what time was it? Right, okay, it's 2:10 now. I think what we'll do, that's a good bit before we start the next section. I'll just do a couple of questions, and then we'll go for a tea break again. Good old tea break. You can never have enough of cups of tea. Well, you can have too many, in my case. Okay. Throttle checks. We've got the break-off, pull-out checks. So just go back the way. How much pressure are we looking at, roughly, for a break-off, pull-out check in pounds-feet?
1.5 and 4.5.
Yeah, good.
Yeah. Out of 15 or 45.
Yeah, that's good. That's a bonus point. That's a bonus point. With the throttle controls, obviously, we get a mechanical bounce at throttle controls. When you push the throttle forward, it will stop, and there's always a little gap. Hence why you leave that 1/8 of an inch gap. You'll get a little bounce. Now, modern aircraft, you're flying by wire, so there's no physical connection. It's all electronics, wires. But we do leave a little bit of bounce. It's almost like a pretend action for the throttles, for the pilot to feel that bounce. It's more a confidence thing. So when you've got fadeate controlled throttles, which is all electronic, we still have a little bit of bounce mechanically on the throttle lever, although physically it's not doing the bounce to the engine because it's all fly-by-wire. But it's just to give that same sense of feel. Yeah, I'll spend that one. Okay, if I want to change the location of the range of a throttle, what would I adjust? Would it be the radius or the length?
Radius, if we want
Radius.
range.
Other one.
Or
Yeah, if we change the radius, if I change the radius, I open the gap or decrease or open the gap of how much that throttle moves. Yeah, that's the radius. If I change the length, it's where that whole section starts and stops.
Yeah.
Okay, we don't change the amount here. Radius, yeah, the radius changes the amount. The length changes the position that amount stops and starts. So you can actually move the throttle levers to make in line without changing the whole range, if that makes sense. Yeah. So the distance the throttle moves is the radius. Where that starts and stops from is the length. Does that make sense? Sort of. All right. What does auto throttle do? Two main things, two main purposes. Auto throttle.
maintain the constant air speed
Yeah.
and to
During
close throttles at a constant rate of during flare.
flare. Yeah. Is everybody happy with flare? Flare is just the angle of attack as you're coming into land. Yeah. Or indeed taking off something, but usually for coming into land. Good, good, good. Right. Quick one for tea break. If I said to you, let's go back to the fuel system, just to throw one in. If I said to you, is that you laughing or crying?
I guess both.
Tears of joy, that's what it is. Tears of joy, learning module 15 and fuel systems. Okay, if I said to you the upstream pressure on the pressure drop control diaphragm has decreased, what's going to happen to the spill valve? Will it close or open? So the upstream pressure of the throttle has decreased. What's going to happen to the spill valve? Will it close?
Close.
Open.
Oh, we've got two.
Close.
It will close.
Close.
Yeah.
It will close.
Two close.
Yeah.
Three close. Any more bets?
It will close.
Anybody else? Close. Yeah. Anybody else?
Question, please.
If your upstream pressure in the throttle decreases, what will happen to the spill valve? Will it open or close?
Close. It will close the spill valve.
Good. So because the
So
spill
that
valve,
it will increase the pump servo pressure.
fantastic. Our job is done, gentlemen. We've got there. Okay. Does that sort of make sense now? What's happening? That's just to do with the throttle differential pressure. Yeah. We open the throttle, we make a hole, we decrease pressure. So that's going to shut the spill valve because the spring is going to move the valve up. Close servo pressure, which will increase the pressure, increase pump output. Good. Good. And that's bang on about 1/4 now from me. Okay, let's go for a tea break and then we'll move on for a little bit more today. We weren't too far ahead. We're going to supervisory engine control and a little bit of FADEC. Again, we won't go too far. In fact, okay, guys, ready for another part. Moving on to supervisory engine control. Just get this bit sorted out. Okay. Right. Oh, there we go. Okay. Right, so as well as mechanical control, obviously a lot of things now are fly-by-wire. We did have some basic electronic control looked at earlier, and we're going to look at some various versions of electronic control. More gas turbine, turboprop engines will have some form of electrical engine control. We saw a very brief one there with the amplifier for the LP spool speed and obviously EGT as well. So some systems we're going to look at in this section. I'll look at electronic control. I'm going to look at electronic control amplifiers, engine supervisory control, commonly known as ESC, fuel authority fuel control, commonly known as FAFC, and the one I've already sort of mentioned briefly is good old FADEC. Okay, fuel authority digital engine control. Now, basic electronic control, sorry, is a system has a computer fed information from various engine sensors and will operate what's called a hydromechanical fuel control unit. So basically a fuel mechanical system, so as to maintain engine effectiveness over the full throttle range. So look in the back there, you'll have your EGT sensor, like we saw in the fuel control system. That will go back to an engine computer, and then finally that will decide what to do to the, or information to give to the fuel control unit, and that goes all up to the engine, and then again it's just a loop system. Okay, so it's a mechanical fuel control unit, sensor from EGT, reference data, and then the pump of the fuel control unit will decide on how much to put into the engine. Well, that's a basic electronic control. Control amplifier, basic sort of system again. Oh, excuse me, it's on down the way. Again, you'll have your exhaust gas temperature sensor. Again, this system has an amplifier which receives the gas temperature EGT signal and also your engine spool speed, compares that information to the engine stand limits, and if any exceeded, it will send a signal to the solenoid we saw before in the fuel control circuit to open the spill valve, and obviously reduce the fuel input to the burners. So again, there you have your exhaust sensor, the amplifier, engine RPM we looked at, all goes to the signals there. Again, back to your fuel control unit as well. So that's a basic electronic control amplifier. Engine supervisory control, or abbreviated to ESC. Supervisory control will use in conjunction with your EPR, or engine pressure ratio. We'll come out a bit later on, but basically what that is the pressure at the back of the engine against the pressure in the front of the engine. So it's comparing the pressure. Again, ESC, or engine supervisory control, looks at N1, EGT, and also the EPR, the engine pressure ratio. Compares all those figures with a reference, and that is taken from the ADC, the Air Data Computer. So the Air Data Computer holds all the information of what it should be happening. Then the real information in real time, what's actually happening with the engine, is compared to that, and then depending on what the situation is, will increase the fuel flow as required or not at all, depending. Okay, so you've got front pressure, the engine pressure ratio, and your back pressure. That goes to your ESC. Reference from the Air Data Computer gets its information from there. And also your throttle lever angle, you're commonly known as TLA. All right, so other inputs, the TLA, bleed air as well. Again, it's the bleed positions. You need to know the position of VSVs, etc., and that sort of thing. Close the bleed valve. And again, that will go to the fuel control unit, which will eventually send the fuel to the burners. So a lot of things, a lot of inputs going in there, and that's engine supervisory control. Always comparing with the reference material or the data that's informed on your ADC. If it exceeds that, it will reduce the fuel accordingly. Okay. Full throttle fuel control, nice simple one, this one. This is full control of the engine's fuel control unit only. But like FEDEC, it controls the engine all over the system, inputs including airflow control as well. So all we've got is full throttle fuel control and the fuel control unit. Its primary job is purely controlling the fuel. FEDEC is in charge of everything, including the fuel, the FAFC and bleed valves and that sort of stuff. But FAFC is only there for the fuel. Okay, just admitting another guy there. Get back to that one. All right, so nice simple one. FEDEC is in charge of everything. FAFC, or full throttle fuel control, is purely in charge of fuel only. So we've got a FEDEC digital engine control system, FEDEC throttle control. That's just a basic graph of what's going on there. So FEDEC control system, again, it's all fly-by-wire as we call it. There's no mechanical linkage. Again, the control is all done using electrical signals, but it has to fulfill the same task as the same job as a mechanical one. Full throttle range, bounce at the max stop, etc. And also the stagger check are within current limits. Okay, so that's just showing you here various bits and pieces that the FEDEC's looking at all the time. Okay. Other things you might be looking at, FEDEC is basically the brains of the engine. It's the computer that controls what is happening, irrespective of what the pilot wants. The pilot might say, I want full throttle, but the FEDEC will decide if they can do that or not do that. Okay, so you've got things like power management control, starting, shutdown, ignition control, fuel control, thrust reverse control, variable geometry control, active clearance control. We'll cover those later on. All goes through the brains of the system. Yeah. Basic FEDEC system we've got there, we class it as a closed loop system. Okay, and what I mean by that is we've got information going out, but we're also getting information coming back into the FEDEC system. Now we class it as a closed loop, fully redundant system. In other words, it's self-maintaining, it looks after itself. Yes, it needs to be tested every so often, but when it's working perfect, it looks after itself. It needs no other information or help from any outside sources. We'll have the pilot's input, your throttle lever angle. Okay, the fuel control will provide the fuel to the engine. But again, we're getting main two signals are EPR, engine pressure ratio, and your N1 signal, as well as your TLA. All goes to the computer. That will say yes or no. and give the information to the fuel to do its job. Okay. All right. Again, moving on to that, you will have FADEC engines will have 2 FADECs per engine normally. On a piston engine, it's 1 FADEC with 2 channels, but we class this as 2 FADECs. Some aircraft just have 1 FADEC with 2 channels, but basically we've got 2 FADECs classified as Channel A and Channel B. Now you see that both these channels, they're both looking at N1 and EPR. Okay. They're both getting information from the ADC, the air data. They're both getting information from the TLA, the throttle lever angle. And they will give, one will give information out to compressor control, okay, and it's likewise with B, but they cross over. Okay, we've got fuel control on one side to the meeting unit, and we're crossing over to compressor variable geometry. What you will find is one FADEC will be doing most of the work, and FADEC B will be sitting in the background, sort of chilling, keeping an eye on things, just in case FADEC A fails. But they cross over to compensate and look after each other should that happen. So as well as fuel control, they also control the airflow control systems, VIGVs, VSVs, bleed valves, etc., and all other bits and pieces that go with that as well. Demand signal will come into the FADEC, it'll look at information, and then obviously adjust the fuel flow as required through the FAC system as well. So it orders the fuel pump and the meeting unit, and then the required amount of fuel will allow the engine to accelerate. Again, as it's getting the feedback from sensors like EPR, EGT, N1, and a lot of good stuff, it will maintain the correct system at the correct time. So a typical FADEC system, there we go. There's your computer. Looking at Mach, altitude, forward speed, temperature, etc. FADEC's in charge. Your CVG, engine, and then feedback from the engine. So that's a sort of typical setup. Okay, so changes like we saw, we're looking at the fuel system for altitude, forward speed, temperature of the day, and that sort of thing will all be compared through the ADC, and a reference will be made to that, and then the FADEC will say, okay, this is the fuel you can have for that period of time, or not at all. Okay, so there's quite a lot going on, all in the split second of an eye. FADEC is more consistent, quicker, more effective than a pilot can be, so that the FADEC can make decisions far, far quicker than a human being can do, and so it will provide the most efficient route, efficient fuel supply where possible. Basically, it reduces the workload on the aircrew, makes flying hopefully a bit better. Standard modern aircraft have the FADEC linked to your ADC. Okay, and that is an integrated control system. Most of these systems are set up as a majority what's called a win circuit, so the highest win wins. Information from the ADC received from the FADEC about the engine is then displayed in the cockpit in your ICAS, engineers indicating crew alerting system. Basically, your digital screen, that's what that is. It's all the information, because old days, gauges would be analog gauges, needles and that sort of thing. Nowadays, it's all digital, LCD screens, etc. Okay. So basic overview, there's your aircraft. We've got engine 1 with 2 FADECs, engine 2 with 2 FADECs, both looking at each other. Okay, and we've also got what's called a CCDL. Now, CCDL stands for a cross-channel data link. So as it sounds, it's a cross-channel. They're looking at each other's FADECs, so each engine, 2 FADECs, share data using a cross-channel data link with the FADECs on the other engine and also with the aircraft. Okay, only 1 FADEC per engine is in charge, but as I said already, should that one fail, then B will take over. But they are looking at other parameters on other engines. Now, the reason for that is if you have a complete engine failure, or if both FADECs fail, then potentially we can maybe borrow some information from one other ones. Not always, it depends on the engine type you got, the aircraft type, but it can vary. But that's a very basic oversight of that. Okay. Okay. Diagram there shows inputs and outputs to one engine and 1 FADEC. So we've got 1 FADEC control in the middle here. Okay, we've got engine crew or ICAS system, your engine indicating crew lighting system, your ADC, your thrust lever, cockpit discretes, aircraft relays, ID jumpers, etc., aircraft power supply, FADEC B, engine sensors, the list goes on and on, you know, CVG and all that good stuff, ignition. So there's a lot of information. You can imagine a pilot trying to look after all that in one go, it's too much. So the computer takes all that away from them and makes it far easier to fly. And we're going to speak about cockpit discretes and aircraft discretes very shortly. So some of the inputs we're going to look at. You can see there we've got up the top, got an internacelle, that's a buzz exchange with a power supply and things like FADEC, thrust reverse and all that good stuff. Then we've got air data. Air data looking at pressure, altitude, Mach number, indicator speed, total aircraft temperature, again all via the computer. Now the main ones obviously looking at is the TLA, the thrust lever angle. Okay. Cockpit discretes. Now a discrete is just a very posh name for a switch. Okay, a cockpit discrete is a switch that you or the pilot can physically move. Okay, so that would class as a cockpit discrete. Some examples there, we've got thrust ratings, takeoff, climb, cruise, maximum continuous. We've got engine start-stop switches, ignition on and off switches, anti-ice on and off, FADEC reset to clear faults, and alternate FADEC select, so between channels MBs. That's physical switches that you or the pilot or an engineer can physically move. Aircraft discrete, well, we can't do that physically. So these are micro switches. Things like weight on wheel switch, so when the weight on wheel engages, the micro switch is made. Landing gear down, again, a micro switch, thrust reverse deployed, a micro switch, thrust reverse stowed. So these are switches that are activated by mechanical inputs on the aircraft. In other words, switches that a human being can't physically move. So that's the difference between a cockpit discrete and an aircraft discrete. Basically, switches, whether they are manual ones by a person or mechanically done by the aircraft itself. Some other inputs might have is engine sensors. We've got N1, primary fan, secondary fan, depending on the engine. N2, which would be a HP spool. T2.5, well, that's the 5th stage. Remember, if you go to your annotations, that would be inlet temperature and pressure. ITT, interstage turbine temperature. Again, we're starting to use abbreviations more now. P0, we've done that already. That's outside air temperature and pressure. T0, P0. And CVG position as well. Yeah, the FADEC needs to know the position of that. We're going to look at a thing called FPMU. More abbreviations, lots of abbreviations today. Now, the FPMU is a main metering valve. Okay, position for a linear variable induction transducer. Now, the linear variable induction transducer provides the feedback. Okay, now what I was going to add there, all discretes have a 10 kilo ohm resistor across the contacts. So all discretes, and they're supplied with current limited for voltage, so it allows the FADEC to detect an open or a short circuit condition in the aircraft engine one. So quite having a resistor in there. If you don't have a resistor in there, the signal can be lost very quick, which short circuit and open circuit. But having a resistor in there, that gives enough time for the FADEC to say, wait a minute, I think I've got an open circuit here, or I've got a short circuit, and it will adjust accordingly. Give an engine warning as well. Okay. Let's change that bit there. Okay, so discrete signals and TLA, etc., FADEC, an engine, you have a PMA, a permanent magnet alternator, provides the power. Section of the ADC aircraft interface, you have your independent aircraft power supply as well. So even with aircraft power failure, the pilot would still control the engines in the normal way, i.e. through your FADEC. They have a certain power supply. Okay, so there we go. All discrete signals have a 10K resistor across the contacts to ensure and find out if an open or short circuit. Okay. Some outputs, pretty much similar to what we've got already. You've got internacelle as normal, you get ICAS, alternate FADEC, in other words, which FADEC's in control. And these are hardwire signals, including the CCDL, aircraft relays, starter shutoff for the speed of your HP spool, environmental, ECS, etc. And your fuel pump metering unit again, latching shutoff valve, CVG, there's a lot of things it's looking at. Some outputs, again, ignition igniter, yeah, actually switching the spark plug on. And we'll look at a thing called active clearance control, which I'll come on to shortly. Each engine control system has 4 harnesses, 4 bunches of cables. So in other words, 2 designated for internal, which are clamped to the right and left side of the high pressure compressor. 2 are designated external, again routed right and left of the engine. So you've got 4 harnesses there. Okay. The harnesses are obviously labelled A or B and dedicated to the corresponding FADEC it's in control. And that's a basic, typical layout. So there's FADEC A, there's FADEC B, okay? And you have all the inputs and outputs, the power supplies, control panels, etc. There's your pilot's lever in the middle, and you've got you obviously going to FADEC A or FADEC B. There's your cross-channel data link, so they can look at each FADEC to keep an observation of what's going on. And again, your power supplies and the various engine sensors, actuators like for CVG, etc., and your VSVs and all that good stuff. So it's a typical sort of layout. So each FADEC needs a power supply, and 2 main power supplies there. One from your PMA, your permanent magnet alternator, like an alternator in a car, and obviously one from your 28 volts DC standard supply from the aircraft side. Now, during engine start, the central buzz bar, it's not a bus, it's a buzz bar, provides power, but as engine speed increases, the PMA output increases and is automatically connected to the FADEC power supply at 50% N2. In other words, when the HP spool reaches 50%, the PMA is automatically connected. So we're running off standard DC supply, then the PMA will kick in at 50%. So simplified diagram there above, what we've got is got things like speed request, TLA inputs, fuel flow, G, main metering valve, throttle feedback, all that good stuff, main metering valve position, and all that as well, CVG, etc. Again, what we're looking at there, fan speed N1. Okay, looking at things. Oh, I'll change it over. Oh, this has gone dead. Closed loop control, set the fan speed equal to that computed thrust, and then we'll have various logics, CVG settings, etc. Again, all controlled by good old FADEC. Engine auto starting as well, we'll look at that. So there's quite a lot: acceleration, deceleration, fan speeds, various bits and pieces there as well. I'll just double check in there. Okay. Now, one of the most important things is engine protection during shutdown or for shutdown. So I mentioned just before break about the LP fan maybe going over speed, and your limiter would kick in, reducing or opening the spill valve to reduce the fuel flow. So what we've got here, if your N1 speed should reach or exceed 105%, which is roughly just over 9,000 RPM, or your N2 is your HP spool should go 105.5%, which is roughly about 17,000 RPM. The overspeed logic shuts down the engine only if both FADECs agree, because there might be a slight fault with one FADEC, and another FADEC's going, wait a minute, I don't agree with that. So there's no point shutting down the engine if it's okay, it's just maybe a fault with the FADEC. So they must both agree before they shut down. It's like having a computer having its own duplicate check, if that makes sense. Engine shutdown also occurs if N2 is less than 54%, which is about 8,500 RPM. That's just slightly less than what's called self-sustaining. When we start an engine up, if the speed drops below self-sustaining speed, well, the engine's going too slow. And if you've got fuel going in a very slow engine, there's a chance it's going to overheat and cause damage. So if it senses the engine's going below about 56, 58%, thereabouts, it'll say, that's too slow for me, I'm going to shut the engine down. Okay. Okay, any questions before we move on to ignition? So there's a lot of inputs and outputs. I'm just going through some of the basic stuff. You can read through some of the more bits, but we'll recap a lot of these ones, so don't worry too much there. Power supply is done. Shutdown is good. Ignition, yeah, let's have a look at the ignition. Any questions, guys, before we move on? Everybody all good? Everybody still awake? Just
Yeah, it's all good.
all good, good. That's not too bad. Okay. Right, let's move on to the next bit. So fade ignition. I've got a simple fade ignition setup there. My mouse is playing up again. Okay. All right. So simple fade ignition. Each engine we've got sort of representing there is classed of a dual, what's called a dual redundant ignition system, comprising 2 igniters or ignition spark plugs, 2 high tension ignition leads, or 2 igniters, and each exciter is controlled by a separate FADEC. So as we've got a FADEC there, we'll call it FADEC A and FADEC B. There's your power supply, your PMA. Okay, here's your exciter, the one that actually provides the power to boost the power up to have your spark plug. There's your spark plug or igniter. Here's your HT leads. We'll have some sort of LT lead here, low tension and high tension leads. What sort of symbol is that, do you think? For me, electronics, module 3, module 2, possibly, definitely module 3. Basic electronics, what does that symbol represent?
Transducer.
Say again, sorry? What does that symbol mean? Yeah, it's a transformer. You're going to boost the power supply. We're getting your power from your possibly magnet or the permanent magnet, or it could be standard 20 volts DC. It could be 115 volts AC, possibly, depending on the system. But we need to step up. We're going to look at ignition circuits more in depth later on. But for a basic one, we get power in, step the power up, control it, and then send it to the spark plug. Now, the FADEC will determine when that sparks, and usually on ground starts, only 1 igniter is used. On the older engines, we would have 2 igniters per engine going crack, 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 crack. Okay. Some of your engines now, they just need 1 igniter working. If that one fails, then you want to start an engine. You'll switch, the other one will switch over. Okay. But we have usually 2 igniters per engine, but only 1 will be working at each time. And they will alternate. So it will have in its memory that on one day it started the engine with the left igniter. So the next time it starts, it will start the engine with the right hand igniter. It just saves a bit of wear on the igniters. Okay. Prime supply for ignition is usually a single phase winding in your PMA, which provides roughly 20 to 40 volts AC at all N2 speeds, so your HP spool above 10% power, and stored in capacitor. And we discharge it roughly 4 to 7 times a minute. There we go. Single phase winding, 20 to 40 volts, all N2 above 10%. There's no point in putting ignition on below 10% because we've not got rotation. If we've not got rotation, then there's no point in putting ignition on. If we've got no rotation, there's no point in putting fuel in. So it's a safety as well. We need to get 10% rotation before we can actually, it's worthwhile putting engine speed in. Power storing capacitor, yeah, discharge 4 to 7 times per second. Relays on diagrams are shown de-energized, which gives what's called an ignition on condition. So just in case you get a failure, we've always got a power supply of some variety available. So that's a fail-safe arrangement. We don't have to physically switch it on. If the FADEC's working correctly, it will be in the on condition. Ignition switches on the power plant control panel mounted over a panel can always be set to one of 3 positions. Oh, excuse me. First position is the on position, and what we have there is power is removed from an exciter relay, and continuous ignition operation takes place as a safety precaution when flame out is possible. Again, you might be flying through some turbulent weather, harsh conditions, so a chance of maybe flame out. So we need that ignition system on, ready to go for relight. Auto, that's the next position. Again, the exciter relay is de-energized during startup to provide spark necessary to begin combustion. And once combustion is established, the relay is energized, therefore removing the supply to the igniters. So it sounds a bit back to front, okay? But it's just the way the electrics work in there. If a combustion fails in the air, the FADEC adjusts the fuel flow and the compressor variable geometry. So it'll be moving your VSVs and your VIGVs. Then energizes the ignition for an automatic relight. So it's doing this without the pilot even thinking, to be honest. When you go in auto, you can switch it to auto if the pilot thinks going to be flying through some, terrible weather and that sort of thing. On the ground, the FADEC will initiate an automatic shutdown if no combustion is detected. So as it's spinning, and we've got ignition going, we've got fuel flow. If it doesn't get a signal from your EGT gauge or a very low signal, so wait a minute, that's not right. I should be on fire now, and there's no temperature. Then there's no point in me having a spark. There's no point in me putting fuel in. So the FADEC will shut down the engine. Okay. Now, important thing with that, if a FADEC does automatically shut down the engine, make sure you switch the start light to off, because if you leave it in auto or whatever, it will try and start up again on its own. So again, you have to watch out for that. Okay. Get the stock again. This is the last one. The FADEC energizes the exciter. So energize the exciter, which cancels out the ignition itself. And there's your basic auto start. So you got your two FADECs, you've got your TLA, inputs from the aircraft system, outputs the aircraft system. Again, same for channel B, inputs from the aircraft system, outputs from the aircraft, and your TLA as well. So they both look at the same thing. A is looking at hydromechanical fuel unit, start valves, thrust reverse, ignition, again, and B is looking at all those as well as checking each parameter. Now, when the engine's starting up, channel A is obviously control normally, B is watching for surge and other characteristics that potentially could be a damaging start. So B will take over just in case FADEC A has missed something. It's just chilling in the background, having a bit of a chill, but it's keeping an eye on what's happening during the engine start, just in case something disastrous goes wrong. Okay, that's the typical sort of auto start setup. All right, let's have a look. Where are we there? Who's up there? All right, so thrust rating modes. What we'll do is, we'll do thrust reverse modes and FADEC switching, and then we'll look at the control system after break time. So we need certain thrust modes. Old days, we didn't have that. We didn't have FADEC, which is a mechanical pilot's input, how much throttle was required for takeoff. So it's up to the pilot to decide how much cargo they've got, how much fuel, etc., etc. But we can actually input some information into the computer. Computer will decide, okay, this is how much percentage of throttle you need, and we can use what's called thrust modes. First one is TO. It is called maximum takeoff, and that's 100% N1, so 100% LP spool speed. Makes sense. You're taking off, you want 100% power. One is maximum continuous. It's a bit less now. You're looking at 86% N1. LB is maximum climb, so it's 76 N1. Now, maximum climb, that'd be when you maybe just want to gently climb up. You're already at altitude. You might be changing up to a higher altitude, but you don't need 100%. You just need a little bit extra called max climb. So you can switch that to there. CRZ, or maximum cruise. Again, you're just sitting with your altitude, desired altitude, and you've got it in 5th gear, right? You're just having the RPM, chilling away about 70%. You don't need it to be sitting at 100%, so you can actually select the thrust modes required, and that will move the throttles to the correct setting. Again, that leaves the pilot to go to sleep and have a cup of tea. Okay. So example thrust rating requirements. FADEC will select takeoff mode if any one of the following conditions are met. FADEC power up and power interruption. Takeoff mode button is pressed, also by the pilot. Thrust lever is moved beyond the thrust set position. So you might have a thrust position and you move the throttle lever forward. That overrides the setting. So if it goes, oh, wait a minute, he's looking for more power, we'll go to maximum power, takeoff power. And the gear down and locked below 15,000 feet. Now, if you're geared down locked, you come to land. So why do you need full power for landing? You should be reducing power, shouldn't you? But if you come to land and you have to do a roll and take off again, you need to have 100% power available. Okay, so it's a safety thing. Continuous, again, if you press continuous button, this press allows for maximum thrust for given ambient conditions. So depending on the ambient conditions. For climb, mode will be falling condition again. If you press the button, allows for maximum thrust for given ambient conditions. Cruise, when the con button is pressed, there should be cruise button, sorry, when both engines are running. Okay, now the con, the climb and cruise mode switch inputs are inhibited on the ground. The reason being, you're on the ground. You don't need continuous, you don't need climb, and you certainly don't need cruise. What you do need is takeoff. You need full power available. So when you're on the ground, the weight and wheels is on the weight and wheel switch is engaged, it will disengage that system. Even if you press that system, it's disengaged through the wiring system on there. Okay. And then we'll have a takeoff data store panel as well. We can select ignition selector, fake control, takeoff data store button, engine stop, start and run. Again, depending how many engines you've got. So two controls involved are the takeoff data store button, you input some data, takeoff data set knob, both on the power plant control panel, your PCP, and the following may be set. You can set to takeoff or alternate takeoff, reference takeoff temperature, which is classed as ref to temp, and reference takeoff anti-ice condition. Okay, again, so depending on information, depending on what the flight condition, you can set it as required. Now that's down to the pilot, obviously, to set that. Reset alternate. Let's double check where we are. Yeah, reset alternate. Now reset clears recorded faults unless a fault is currently being detected, in which case you can't clear it. So there's no point clearing a fault because that fault's there. It will keep it live. But if there has been a fault and it's not affecting the engine performance at the moment, it will store that fault. So you guys can go and download the information and find out what's potentially wrong with it. Same as a car, you can plug in a VC recorder, and you can, if you've got a fault with your car, your engine management lights come on, you can plug in a decoder and that will give you a code of potentially what's wrong with your car. And the same for the aircraft. All 10 manual switches that are active and standby FADECs, unless the selected FADEC is not compatible with controlling the engine, where it will do it automatically. But you can physically change the FADEC if required. Why would you do that? Especially for engineers, to make sure that it's working. Otherwise, it would just be automatic by the FADEC. Pilot would have nothing to do with that. So that all 10 overrides automatic switching from active to standby when a fault is detected as well. And the last one yet, reverse thrust. Each FADEC receives the following information. Sorry, it has to know when the reverse system is stowed, because if they aren't stowed, it won't allow it to operate correctly. Deployed, if all thrust reverse doors are deployed, so it will allow you to have a certain power setting up to maybe 50%. And it needs to know if they're both working. If they're both working, remember there will be a fail-safe in thrust reverse. So if one fails, the other one will be brought back in anyway. So you just rely on standard braking. And that takes us up to fuel control systems. Again, that's a good point to stop now and go for another break. And we'll come back in about 20 minutes or so, and we'll do a little bit more and go on to recap, I think. Let's see where we are. What page are we on now? 47, it's about halfway through. Yeah, what we'll do, we'll finish that part off after tea break, and then we shall do, yeah, that'll do for today. We'll do a bit of recap, and then we'll start oil systems tomorrow. Okay, so yeah, same again, guys. Go for about 20-minute break. Come back. The control system itself supplies filtered and measured fuel for combustion, obviously. So, in conjunction, we can also use the fuel to act as hydraulic fluid to operate the CVG system, your compressor variable geometry. The main component of FADEC control fuel system is your fuel pump and metering unit, your FPMU. All right. So, the main component, getting FADEC and the FPMU, and this provides pressurized and metered fuel to a servo-operated, what's called a main metering valve. All right. Servo which is biased to the closed position, so that if there is no torque motor signal from either FADEC, it will cut the fuel to the nozzle. So another sort of safety system as well. Okay. Now the FADEC control metered flow is fed to the fuel nozzles from a pressure raising valve, a PRV, which by spring loading ensures a minimum gear pump pressure at low engine speeds. Feedback, now it needs feedback to know what's going on. So this time it uses what's called a LVIT, a linear variable induction transducer. That's coming there. Okay, so we had an LVDT for the CVG system, and this time we've got for the FPMU, it's an LVIT. Now you've got a thing called a latching two-position shut-off valve. It is stock controlled by two what's called dual coil torque motors. When energized, the FADEC, one of the top motors causes high pressure fuel to port to the backside of the pressure raising valve, and so closing the valve. Other torque motor causes the LV SLV to the latch closed position, and once it has been latch closed, it will remain in that condition until the opposite torque is applied as a result of FADEC control signal, basically when it's energized again. 23% N2, so N2 is your HP spool speed. In the engine start sequence, your LSV valve start solid is energized. Fuel pressure from the LSV to the PRV, lots of V's, okay, hence why we're starting to speak in abbreviations now, is removed. Therefore, it can open the pressure raising valve and allow fuel to be supplied to the main metering valve, which will then pass on to the nozzles. The main metering valve limits how much fuel goes to the nozzles. FADEC control solenoid valve is commanded to open at the initiation of the start sequence. The valve remains closed whenever the solenoid is not energized. When there's no power there, strange enough, it will stay closed. That prevents fuel leakage from the system if the airplane booster pumps are turned on when the engine is not running. If perchance you put booster pumps on and you don't have the engine running, then you could have a possibility of fuel going in via the MFV to the combustors, and it shouldn't be going there. When that's isolated and you do put the booster pumps on, all will happen is the pressure in the booster pumps will build up and just go through a bypass and just keep going round and round. It won't go to the actual burners themselves until this kicks in. And that's your basic control sort of signals there. So I think if I remember right, oh, I didn't put it up there, sorry. Up at the top, there's your LVDT for your CVG. Okay, so your linear variable differential transducer, which just is a feedback signal for the FADEC to tell the FADEC what position your VSVs and your variable IGVs are. Okay, and then for your main metering valve, you have your LVIT. Okay, again, just a sensor feedback from there. So the FADEC control meter fuel flow, it's fed to fuel nozzles, fed pressurizing valve, spring loaded. Again, feedback is therefore from your LV or linear variable inducting transducer. And that's the basic setup. There's the drive from the gearbox, which is turning your pump assembly, which goes to the metering valve, using a pressure raising valve, which will go to shut-off valve, and then both FADECs are looking at the latching shut-off valve, which prevents the fuel from going there just in case. But again, FADEC's looking through everything. CVG, torque motors, other torque motor, air vent valves, it's controlling everything. It's getting lots of sensors back. It's from things like LVDT or your LVIT. If you remember that, a lot of abbreviations, as long as you remember that for FADEC controlling compressive valve geometry CVG, it needs the LVDT transducer. If it's anything to do with the main metering valve, the sensor is the LVIT. Okay, if you only remember those two, you'll be okay for future questions. So with the CVG side of things, what we've got, move that out of the way. Again, there's your CVG taken from that diagram. So CVG activator comprises a series of turnbuckles, torque tube assembly, hydraulic actuator controlled by fuel pressure from the fuel pump. So that's proportional to the speed of the engine. Hydraulic actuator rotates the torque tube, which in turn, by means of levers and turnbuckles, will then move the variable stator vanes into their position all at the same time. Okay, so there's your LVDT. So again, it's controlled by fuel pressure. So the faster the engine's going, again, that will position with feedback from the LVDT to what's going on. So feedback, linear variable transducer will send the information back to the computer, the FADEC, and that will adjust the position of the VSVs accordingly to the engine RPM. That's just a basic setup. It's not the best diagram. Just don't worry too much about it. But that's what's going on. I would try and call that whenever I get a bit of time, try and get a better picture. If you feel free, please copy that and colour it in. Make your own colour code up if you get bored. All right, but basically, there's the whole assembly. There's the drive for the actual unit. There's your CVG actuator, which will move a rod, which is connected to all the VSVs. There's your little LVT sensor, so it gives feedback to the control. Little gear pump, spur gear pump, you've got a centrifugal fuel pump, main metering valve, pressurizing valves, and so on, air start valves, etc. Again, you don't need to remember all these. It's just a basic setup, okay? And then there's your fuel distribution, just an older one. So that is it as far as we shall go today. Tomorrow we shall start on engine lubrication system, oil systems. Okay, so I won't start that today. That will be tomorrow. So the next few minutes, what we'll do is we'll do a bit of recap. All right, we'll just go back away again, see where we were. All right. So just where we started from then, who can tell me what the sensor is called for feedback for the main metering valve? What sensor is it? Choice of two. They both start with L and both end in T, but which one is it?
What was the question?
What is the sensor that gives information or feedback to FADEC on the position of the main
LVDT.
valve? Close. Other one?
LVIT.
LVIT, yeah. So for the main metering valve, it's the LVIT. For compressor variable geometry or CVG, it's the LVDT.
LVDT. Yeah.
Okay. I think this is in your old books as well. It's probably worth highlighting that. Once you get the new books, highlight it and move it across. If you remember those two, we'll be fine. Okay. Which thrust modes are inhibited or isolated on the ground?
Is reverse thrust?
No, you can have reverse thrust on the ground. So we're looking at thrust modes. There's 4 thrust modes, and there's 3 of them are isolated when you're on the ground or inhibited.
CRZ.
Yes, CRZ, cruise, that's one of them. What else have we got?
What was the question?
You've got 4 thrust modes, right?
Yeah.
But on the ground, we don't need 3 of them because we're on the ground. We need one of them definitely for taking off. Well, there's one. There's takeoff. That's one thrust mode. What's the other 3 modes then that we don't use on the ground?
Takeoff, maximum climb, maximum cruise.
And continuous.
Takeoff, yeah, we can take off. So it's the 3 that don't get used on the ground. So takeoff, yes, we need that. We need that available. So what was the other?
CLB,
Maximum
CRZ.
continuous, climb, and
Yeah,
cruise.
climb, continuous, and cruise. Yeah, because we need power on the ground. Once we get up to where we're going, yes, we can switch other ones on. But at the moment, continuous climbing crews are inhibited on the ground when we've got a weight and wheel switch. Okay. What is the primary supply of power for ignition system in a single phase PMA? What power does it supply? Voltage.
Question?
So we've got what voltage does the permanent magnet supply at all N2 speeds above 10%? What's the voltage it supplies?
20 to 40.
What is it?
Yeah, 20 to 40 volts AC. When we look at ignition circuits later on, we'll do a generalization. It'll be more 20 volts DC or maybe 100 volts AC permanent system. But for FADEC, use a PMA. Yeah, good. All right. How many igniters are used on startup? One or two?
Sir,
One.
question is clear.
Yeah, just the one igniter. And we shut the engine down. The next time the engine starts up, they'll use the other igniter. There's always two igniters on an engine. There's only one gets used on the first startup. When it shuts down, say it's the left-hand one, that'll be used when the engine shuts down and then starts again. We'll use the right-hand igniter instead of having two going. On some of the older engines, we'd have two igniters going opposite all the time. But again, that just wore them out quicker. So they found that just having one, and you'll soon know if that's not working because it won't start. Okay. Good. Okay. With reference to engine protection shutdown, so an engine will shut down at certain percentages. Okay. You remember what they were? For N1 and N2. There was 3 times.
105%.
N1 should not exceed, should 105 into 105.5.
Yeah. And N2.
And both FedEx should agree.
Yeah, both they should agree. Yeah. So that's right. And also, if it's less than 54%. Yeah.
Yeah.
Good. Good.
Yeah.
Okay, power supply. What's your standard power supply before the permanent magnet kicks in? What's the standard voltage?
28.
28 volts
yeah.
DC. Yeah, the FADEC, because initially it'll get 20 volts DC from the bus bar, and then it switches over at what percentage N2?
50% N2.
Yeah, 50%. Once you use 50%, then the permanent magnet is going fast enough to produce your 3 phases. Okay, and that'll supply your power accordingly. Okay. A moment. What is a discrete? What is a discrete?
Signal.
Cockpit. You mean cockpit discrete?
Yeah, you get cockpit discrete and get aircraft discretes. What's the difference between the two?
The cockpit discrete means the information you are getting in cockpit.
Not information you're getting. You are in the cockpit, but what's the difference between an aircraft discrete and a cockpit discrete? Physically. Anybody?
Cockpit discrete, engine start off, ignition off, on.
Yeah, so it's a manual switch, which is activated by the engineer or the pilot. Yeah. So a cockpit discrete is physically moved by somebody, whereas an aircraft discrete is automatically by a micro switch. So it's something you can't switch. It's up to the aircraft, like a weight on wheel switch. Yeah. Reverse thrust bucket switch and that sort of thing. That's an aircraft discrete. It's just they're both switches. One is moved by a human and one is moved by the aircraft. Okay. What does CCDL stand for? What does CCDL stand for?
CCD.
CCDL.
Cross-sectional
data link.
Yeah. So it's basically a crossover. So FADEC A can look at FADEC B, and FADEC B can look at FADEC A. Cross-channel data link. Good.
data link.
Okay. The FADEC gets sensors back from the engine, and it has to use a reference to compare that information, the real information, to the theory information. Where's that data or theory information stored? Or where does the FADEC find that information?
On the ADC.
Yeah, ADC, which is your air data computer. Yeah, good. What do we class a FADEC system as? What do we actually call that FADEC? What's it classed as?
Engine.
Yes, it's the brains of engine, yeah. What's the more technical name for it?
Electronic engine control unit.
It's a control unit. If I say, I can't say that. If I gave you an option of open or closed loop. Is it an open loop system or a closed loop system?
Closed is closed.
Yeah. Closed loop because information is going out, but it's needing information to come back in again, yeah? And we call that a fully redundant closed loop system. That's what I was looking for. That's the type of system a FADEC is. It's fully redundant. In other words, it looks after itself, and it's a closed loop system. So information goes out, information comes back, okay, and compares against the ADC. A fully redundant closed loop system. Okay. What are some of the basic parameters? 3 basic parameters a typical FADEC will look at. So 3 basic bits of information that the FADEC needs to know.
Engine speed.
Yeah, engine speed. Which one? Will that be N1 or N2?
N1.
N1, yeah. You can have N2. Some engines will have N2, but definitely N1. If that's going too fast, then the engine's in trouble. What about if I gave you a clue, front and back? There's a clue. What's at the front, what's at the back of the engine? It needs to compare.
Pressure ratio.
Yeah, engine pressure ratio, which is exhaust pressure over inlet pressure. Good. And also, what else might it look at? Just for something else, it needs to know the position of.
Bleed valve.
Well, yeah, it could do. That's a bit more down the line, but essentially, what does it need to know straight away? You've got EPR, LP speed, and what else? If I said TLA, what does that mean?
Thrust lever angle.
Yeah, or throttle lever angle. Yeah, whatever the pilot or yourself is doing with the throttle, it needs to know the position of that. So it can compare it against the data, compare it to what's happening with the actual engine at the time as well, and especially on startup. Okay. And that's pretty much an engine supervised control system, an ESC there. Which system is only looking at fuel? Or which system only controls the fuel?
FCU?
But FCU is part of it, but there's a system that controls the FCU.
Fuel metering unit.
No, that's part of it, but there's a whole system that
FAFC.
controls it. Let's say again?
FAFC.
Yeah, FAFC, Full Authority Fuel Control. Its only job is to look after the fuel system, whereas FADEC looks after that and everything else, yeah? So that's to do with supervised control. So FAFC or FAFC is purely for fuel control. Good, good, good. Good, good, good. Okay, just going back away a bit again. Breakout pull-off checks on your throttle levers. What was the average sort of pressure required? So you're using the spring balance. What was the pressure required to move the throttles? Pounds feet. How many pounds feet was it?
Sorry?
How many pounds feet? Now we're doing put the spring balance on the throttles. There should be a certain amount of force. So how many pounds feet was it? It should be between so much pounds feet and so much pounds feet. What was the numbers for moving a throttle lever using a spring balance?
One and a half and 4 1.5.
Yeah, good. 1.5 and 4.5. Good. What was the minimum gap that should be when you're doing the control rigging of the throttles? The gap should be the maximum stop of the throttle lever.
1/8.
1/8 of an inch. Yeah, it was about 3 millimeters. Good. Good, good, good. If I change the radius of a rigging of the throttle lever, what am I changing?
Range.
Reference.
Amount of things.
Yeah, the amount of the range. Good. So if I change the length of
Location
the
of range.
location, good. Always good. What was control creep?
Prevent friction damper. Is
Yeah, we fit a damper because due to vibration of the aircraft, the throttle controls, if you don't have your hand on them, they can start vibrating back down to idle. So if I put a little damper on there, we can stop that happening. Yeah. Auto throttle had two main purposes, which were what?
maintain constant air speed
Yeah. During
localizer or glide path phase
yeah,
of
good.
the automatic landing ILS or
Yeah, yeah. And the other one?
Was
other.
the throttle at constant rate during flare.
Doing very good. Brilliant. Very good stuff. Okay, doke. Right. Right, I'll give you the option. Do you want some questions on the pressure drop control, dashboard throttle, pilot's input, ambient conditions, spill valves, fuel pumps, or do you want that first thing tomorrow morning?
We want with options.
The
Yeah.
options are, I'll give you the questions now, or I'll give you those questions first thing tomorrow morning.
Okay, yes, we want it. Tomorrow
You want them
morning.
now, yeah? Oh, tomorrow morning.
Yeah. Okay.
Yeah. Okay, well, have a little read through those tonight. Well, obviously it's late tonight and we don't spend too long. You get some sleep, obviously. But have a quick glance over before you start the class tomorrow. And I'll go through all that fuel system part again very quickly. Some questions before we start the oil system to keep it fresh in your head. Will that be okay?
Yeah.
Okay, that's probably a good bit to stop at today. What time's it? Yes, that's 4 o'clock here, so only about 10-15 minutes. And then what we'll do, we'll recap that fuel part again to make sure we're happy with spill valves, the fuel pump, the kinetic knife valves, etc. We'll make some questions there. And then we'll start on with the oil system. Oil system's nice and straightforward. It's a nice, straight, easy one. It's nothing like the fuel system, thankfully. Okay. So yeah, that's probably a good bit to stop at today. And we'll carry on there. So lots of questions first thing tomorrow. So we'll see how we get on there. Hopefully some of it will stick in your heads tonight when you sleep. You'll be dreaming about fuel systems. I beg to differ. If you are, there's something wrong. Okay, guys, any questions before we head off?
Nope.
No.
Okay, well, enjoy your night and have a good kip. Good night's sleep, and we'll see you fresh tomorrow. Well, I've not seen you yet. I just see your initials as usual, but we'll hear you tomorrow at least. Okay, guys, that's it. If no more questions, all the best, and tomorrow is another day.
Yeah.
Okay. Thank you very much. See you tomorrow.
Okay.
Good night.
Good night.
Good night.
ल केटा हो आज 15 मिनट अगाडि छोड्दैछ तिमीले
हिजो 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 आधा घन्टा अगाडि छोडेको थियो साथी
हाँ?
हिजो आधा घन्टा अगाडि छोडेको थियो हिजो आधा घन्टा अगाडि छोडेको थियो कि
यो फ्युल सिस्टम कसले बुझाउँछ भन्छ तिम्रोमा चाहिँ कसले बुझाउँछ फ्युल सिस्टम
खगेन्द्र सर की जय अनि त खगेन्द्र सर
ताप हान्छ
मैले बुझ्नु